Hello and welcome to my talk about independent block identification in multivariate time series. My name is Magnus Severino and this is a joint work with Florencia Leonardi, Matthias Lopes Rosenfeld, Daniela Rodrigues, and Mariela Suede. So let me start with an example. Here we have the map of Brazil and the highlighted area indicates the location where the São Francisco River is. This is the longest river that runs entirely in the Brazilian territory. It flows from south towards northeast, and along the course of the river there are several stations, these red points here, that measure the amount of water that is flowing in each of these points. So let us call XU the flow that is measured at station U, and here we are considering that there are D stations along the course of the river. And these stations form this d-dimensional x vector, which is indexed by I, where I indicates the time at which these measurements were taken. So the river dynamics may generate independence in the behavior of some points of its course. Say, for example, that there is a point U in the course of the river such that all the measurements taken before this point are independent of those taken after this point. In this particular example, we are saying that we can decompose our original X vector into two smaller blocks of independence. Now, let me define what a set of independence is. We again are considering a d-dimensional X vector following some multivariate distribution function f and giving U a set of indexes that partitionates X into subvectors like this. We will say that U, a set of indexes, is a set of independence for f if the partition of X into yields subvectors that are independent of each other. In this sense, any subset of U will also be a set of independence for F. Moreover, if U and V are sets of independence for F, their union will also be a set of independence for F. This suggests us to define U star as the biggest set of independence for F. And the aim of this work is to estimate U star on the basis of the process X. And by estimating U star, we can decompose X into smaller blocks of independence. Now, given F and a set of indexes U, the U product of F is this decomposition here. And in the particular case, which U is the empty set, we define the U product of F as being F itself. And we can measure the discrepancy between F and its U product by taking this supremum here. In this way, U is a set of independence for F if and only if the discrepancy between U, F, and its U product is equals to 0. Now, since U star is the maximum set of independence for F, we have this property here that says that the discrepancy will be equal to 0 whenever U is in U star, and there is a alpha greater than 0 such that the discrepancy is greater than alpha whenever U is not a subset, is not contained in U star. Thus, U star can be estimated by looking at the biggest set that minimizes a empirical version of this discrepancy between F and its U product. And here we are considering this empirical distribution function here, and we define the penalized cost function, which is a combination of the discrepancy between the empirical distribution function and its U product added to a term of penalty here. And now we define our estimator, which is this one, and U hat will be the set that minimizes the penalized cost function. And now we have the main theoretical result regarding consistency. And it says that our estimator converges eventually almost surely to the true set of independence U star. And this convergence does not require the process to be in a stationary regime. It holds as far as the empirical distribution function f converges to the limiting distribution f at certain rate an, which is related to the penalty term lambda. Moreover, we have this particular result for the IIT case, and under the same conditions of the theorem, if you take the penalty term to be equals this expression here, then our estimator converts eventually almost surely to the true set of independence U star. And finally, we have this result for the case which x it takes values in a discrete alphabet, and if it satisfies this mixing condition here, we also have proven that our estimator converges to the true set of independence for f if under the same assumptions of the theorem, and by taking this value for as the penalty term. Now, our estimator requires us to look over all the possible subsets of U, which is unfeasible even for smaller values of t. So here we introduce a more efficient divide and conquer algorithm to approximate the estimator that we defined before. So in each step, we include a independence point in the estimation of U hat as far as it improves the behavior of the penalized discrepancy. So this binary splitting algorithm constructs a binary tree with nodes indexed by subintervals of the indexes such that the set of terminal nodes of the tree is a partition of the index set, and the endpoints of these trees constructs out the set of the final set of independence. And although this is an approximation to the estimator, we prove that this estimator converts to the true set of independence. Moreover, we also perform simulation on synthetic data to study the performance of this algorithm. And now, finally, if we go back to our original example regarding the San Francisco streamflow data, the question that we want to answer here is can we decompose this d-dimensional vector into smaller blocks of independence? So we run our algorithm with this data, and here we have the distribution of the measurements taken in 10 stations along the course of the river. And our algorithm gives us this set of independence containing only the element 7. It means that we can decompose this 10-dimensional vector into two smaller blocks of independence. The first one containing the entries 1 until entry 7, and the second one with the stations 8, 9, and 10. And if we look into this data, it makes sense to define this as the set of independence, since between station 7 and 8 in the course of the river, there is a hydroelectric dam, the biggest hydroelectric dam in the course of the river. So it makes sense to be 7, the only index in the set of independence. So that's all that I wanted to show to you today. Here are some references that we use to prove our theoretical results. And the last one is this recently published work. So thanks for watching.